We will develop a mathematical expression of volumetric flow rate in a pipe that's conveying fluid such as water under fully developed conditions. So inside the pipe we will take a small cylindrical ring element of that fluid as we will see here in this diagram. So we have a cylindrical ring and it is distance r from the center, and the thickness of that ring is dr. Now if this dr is fairly small, then we can assume that the area of this ring is dA equals the circumference 2 pi r times the thickness of the ring dr. So this is true when we have a very small ring element of thickness dr. So we have dA equals 2 pi r dr. Then the volumetric flow rate we can write as V dot, and by dot we mean it's a rate term. So V dot equals UR times dA. So UR it means that the velocity changes in the radial direction. So velocity is a function of radial direction. That's why we have in parentheses r times dA. So we know that this dA is 2 pi r dr, so we will substitute that. We have V dot equals UR 2 pi r dr. Now we can integrate from the radius r equals 0 all the way to the total radius of the pipe, which is uppercase R. So we have r equal to 0, r equal to capital R, and in the integral we have UR 2 pi r dr. Since 2 and pi are constant, we can take those out of the integral. So we can write equals 2 pi, the integral r is equal to 0 to r is equal to uppercase R, and we have UR r dr. From the previous module where we had developed the velocity profile for the fully developed flow, we will substitute the expression, which was the parabolic expression here. So we have V dot equals 2 pi integral r is equal to 0 to uppercase R, and inside the integral we have delta p r square divided by 4 mu L in parentheses 1 minus lowercase r divided by uppercase R and parentheses with square and end of parentheses times lowercase r dr. Again, you will need to refer to that previous module to see that we had indeed developed this parabolic velocity profile. So now we can go ahead and integrate, but first we will take out some of the constant terms out of the integral. So we have V dot equals 2 pi delta p r square, r, this is the uppercase R, so that's the radius which is constant, divided by 4 mu L. So in the integral we have 0 to r, 1 minus r over uppercase R, parentheses square, and then end of parentheses time r dr. So we can then look at a couple of steps here, so you see how this is all developed. So this equals integral. We will just look at the quantity inside the integral. That is 1 minus r over r square times r. So if we take that r into the parentheses, we will have r minus r cube over capital R square and then dr. And now if we integrate, we know that the integral of r, the lowercase r, is r square over 2 minus, and then the next integrated quantity is r raised to power 4 divided by 4 uppercase R square, and then we will evaluate this from 0 to r, and so we have uppercase R square divided by 2 minus the uppercase R raised to power 4 divided by 4R square. And again, canceling out some of the terms, we have uppercase R square divided by 2 minus uppercase R square divided by 4. And so we can subtract R square over 4 from R square over 2, and we'll be left with R square over 4. And that is the integrated quantity. And of course, we can now multiply that with the terms that we had taken out of the integral. So our volumetric flow rate equals pi into R raised to power 4 delta P over 8 mu L. So this is the expression for the volumetric flow rate. We also know that volumetric flow rate is the average velocity of the fluid times the cross-sectional area. So V equals pi R square times U dash, which refers to the average velocity. Or we can write down the average or mean velocity, U dash equals V over pi R square. Now we just calculated the terms for the volumetric flow rate, so we can substitute the terms for volumetric flow rate, and we get U bar equals pi R4 delta P over pi R square times 8 mu L. Now pi R square will cancel out in numerator and denominator, and we have the mean velocity U bar equals delta P R square over 8 mu L. So in case of a pipe that has a radius uppercase R, when you know the pressure drop delta P, you know the viscosity of the fluid, you know length of the pipe, you can calculate the average velocity using this formula. Now this expression is also called the Poiseuille law. If we are interested to determine the relationship between maximum velocity and average velocity, we can take the equation we had previously obtained for the velocity profile in a pipe, that was UR equals delta P R square divided by 4 mu L in parentheses 1 minus lowercase r over uppercase R square, end of parentheses. So the maximum velocity will be at the center of this pipe, so lowercase r will be 0. Then the U maximum will be delta P R square over 4 mu L, because in the parentheses the R will be 0, and then you have essentially 1 left in the parentheses. So U maximum is delta P R square over 4 mu L, and we have just calculated now that the average velocity U bar is delta P R square over 8 mu L. So we can take the ratio U bar, the average velocity, equals delta P R square over 8 mu L. And now if we divide U bar by U maximum, and we use the quantities that we have just obtained, we will see that we will get delta P R square divided by 8 mu L, and then divided by delta P R square over 4 mu L. So we will get all the terms cancel out, except we'll be left with 1 over 2 or 0.5. So we have U bar divided by U maximum equals 0.5. That means that the average velocity in a pipe, if you have laminar flow, equals half of the maximum velocity. We can also determine this ratio for turbulent flow. That mathematics is a little more complicated, so we will just look at the result, and that is that U bar over U maximum in case of turbulent flow equals 0.82. Again, that can be useful if we want to find out the average velocity based on the maximum velocity in a pipe.